And that's the meanest, like, legitimate thought that I've ever had about Riley and Delilah and Kalisha. Like, it was just awful. Yeah, don't tell them. All right, so fries in the bag. Let's get to it. I'm stuck. Shoot. I don't even know what to do. We're inscribing a rectangle inside of a curve, and we're trying to maximize the area, and we want the dimensions of it. Yuck. Help. Hey, that's reasonable. I'm going to draw the graph. Now, I'm not going to take like crazy amount of time. Is this a smiling or a frowning parabola? Frowning, and what's its y-intercept? 16. So I'm not going to go like crazy with it, but I think that here's my parabola. Roughly, yuck. The first part was pretty good. That's okay. And we're trying to draw a square in this, right? Or not a square, but a rectangle. So I don't know where it is. I'm just going to sketch a rectangle right now. So there's this rectangle that exists, and maybe it's pretty close to what the actual biggest one is. But I mean, keep in mind, it could be this one. That rectangle also exists inscribed within that between the x-axis. But the blue one, I think, has bigger area. Would you agree? They're both inscribed. We're trying to find the biggest one. So here's where we're at. Now, I've drawn the picture to kind of help make sense of it, but I don't have any stinking variables. We're trying to maximize the area, which means I can already think out my primary equation. Kind of. Do you want to put some letters and stuff on here first, or write the primary and then clean it up? Okay. This function is called y, and I'm fine with that. If I want to say this is the value that I'm choosing, and my guess is if you made a mistake, and Sean did awesome on this problem. He stopped in this morning to check it, just so you guys know, and he had everything perfect except one little tiny part that we're going to see if we make the same mistake right now. I'm going to just ask Sean if we make that mistake, don't just shout out the answer to it because it's a really easy one to make. Okay, I don't know what this is. Now, there's a natural thought. What do you want to call this distance? X is a reasonable thought. Is that going to work for us? If I said go to where you're at X, like if I just label this, like what point is this, I guess, maybe is a different way to think about it. It's also X, right? So now there's a little bit of ambiguity. If I just want to say this is X, then this whole distance is what? 2x. Because we're going to plug in x into our function and it always starts from the origin, let's call this x right now, and this would be negative x. It'll be the same on both sides. Now, for this, there's a couple approaches that we can take. If this is x and this is negative x, we can say that the whole base of this thing is 2x. Okay, alternatively, if we don't want to do the whole thing right now, if I didn't want to have to think about that side, could I maximize this area? And then it would probably be how much of the total area? Half. So we have a decision to make. Are we calling the whole base 2x from the get-go? Or do you just want to do it with x and then double it at the end? Do the 2x? Okay, I'm good with that. So here's 2x, and I'm fine with that. And what is this y value, the height of this thing? You could call it y, but there's a better way to write it. This is just 16 minus x squared. So we have a height that's dependent on the x that we pick. From this, now that we have this kind of sorted out, that weird little 2x deal, it will happen over and over. It's so common, in fact, that there's some pretty big theorems later in the year that we'll see. But let's just jump in. I need my primary equation. And the primary equation is where I'm doing what? It's the thing that I'm trying to do something to. I'm going to start trying to walk around more than I do normally. Say that again? I agree with you, but why am I finding the derivative of the primary? It's what I'm trying to, what are these problems called? It could be maximize or it could be minimize. Optimize. We are trying to optimize the area. Let's write a primary equation with area. Now, the awesome thing about this is if we hadn't done all this, you might start with length times width, but there's something really cool. What's my width variable? X is a variable, right? What's the variable in my height? X. We're already all in X, right? So we've naturally just kind of taken care of that secondary equation in this problem. which means my primary, we're already here. The area in terms of x is already accessible. This was my secondary equation, but it just naturally embedded in solving the problem. How do you find the area of this rectangle? Base times height, which is 2x times 16 minus x squared. Okay, if we stop here, what rule do we get to use to find our derivative? Product. Anybody not want to use the product rule? Ooh, I love it. And I don't know if that was Bea or Abigail, but great answer in any case. If we distribute, we can avoid it. 2x cubed. Everybody cool with that? Okay, so there's my true primary. Now notice we can write true primary if you want, but because we didn't have to have a secondary, we don't need it. Now what? Sean, I'm going to pick on you. It is not derive. To derive means to figure out where something comes from, like a formula. There's a different word that we use to take the derivative. We differentiate. Okay, so I'm going to differentiate with respect to what variable? X. Now at this point, I don't know necessarily that you need my help with it. Do you want me to talk through it? Do you guys just want to take over and kick forward? What are you thinking? Okay, I'm going to give you guys like, I don't know, a 2-minute head start. I'm going to start working it as well. Please, please, please. I know the answer is going to be on the board. Don't just wait for me to write the answer. If you're not sure what to do, ask. Let's make sure we can all do this, and we'll come back together. Same thing, ladies on the road. Pause the video here, or JJ, if you're watching, pause the video here, and when you resume, we will see the key. I didn't know any of this before I walked in the door. Awesome. Yeah. Love it. What's A prime? Okay, and when I set this equal to 0, you're going to get the critical numbers. Okay, so just to see this, because these are all calculator-free problems. You can do it without ever touching your calculator. If you, like I didn't specify, so if you used a calculator, you're okay. If I want to solve this, what's the first thing you would divide everything by? 2, and I'll do it to both sides. And I know it's going to look a little bit different, but this is it, right? So I'll add 3, and then I'll divide by 3, and then I'll take the square root. And we get x equals plus or minus the square root of 16 over 3. Or maybe I can clean this up. Keep it here, or do you want to clean it up a little? Okay, so this is maybe going to be annoying. I haven't decided. What's the square root of 16? Is this allowed? 100% for us. Yes, the reason that we don't do this in pre-calc and stuff is because it makes a unit circle awful if we don't clean it up. We can keep this answer. Now, based on this, it doesn't really matter, right? We could have x or we could have negative x. Cool. In either situation, because this is an even function, we're going to get the same area. So it doesn't really matter which one we use. The domain, if we wanted to talk about it, what's the furthest right or left that x could possibly be? Like if I actually want to be able to draw the rectangle, this is a pretty small one. How far over could I come? Where's this number? I didn't identify it, not yet. How do we figure out this number or this number? These are the zeros of which function? That's 4 and negative 4. So as long as my critical numbers are between negative 4 and positive 4, then they make sense. Like that's my domain that we're looking at. Okay. You wouldn't want 0 either, because that would be no rectangle. But here we are. Awesome. And I didn't label them. What are these? Those are my critical numbers. Now we have 2 options. We could use a number line. Anybody switch back to using number lines in first derivative test all the time? Because what's so much easier than using the first derivative test? Oh, my second derivative test. So let's find a double prime. And this is super easy. What is it? Are you negative 12x? Okay. Now I'm going to pick the positive x, so it's going to be easier to work with. Again, it doesn't matter whether we pick the positive or negative. If I pick this positive x, 4 over root 3, and you plug it into this, we'll do, and I like this idea where we're really consistent with it, a double prime of 4 over root 3. Do I care about the actual number? What's the only thing I care about, Sean? If you were to plug in positive 4 over root 3, does it give us a negative or a positive? Negative. Is that good or bad for us? Negative means it's a concave down, so it's like this, and as our critical number, we just found a what? There's a maximum. And we haven't been doing this, but if we need to, and if it clears stuff up, I think it's a good practice. Maximum value happened at x equals what? 4 over root 3. Now, my hope is that I should have been doing this the whole time in hindsight, but we've been doing the maximum part. I just like to specify back it's at this critical number. Okay, do we have the dimensions yet? We're close. We know the width of it is at this x, right? So what's the actual width? 8 over root 3. So I'm going to start writing my end answer, and then we'll come back and we'll get the other part of it. The rectangle of maximum area has dimensions and let's see, we don't have any units, so we'll just say 8 over root 3, and all I did was doubled this, units, by, and now we don't know the y value yet. Could we? How? Hey, let's find y of 4 over root 3. And let's see what this is. 16 minus 4 over root 3 squared. I'm going to give you guys like 30 seconds without a calculator. Give me a number here. I just want to make sure we can do a little bit of this. Awesome. Baker, did you get approximately, hold on, lost my train of thought, 10.669? Awesome. Or an exact answer, because Baker just did the approximation in his head. What did you guys come up with? 32 over what? 32 over 3? Which, gosh, that is 10 and 2/3. Awesome. Nice job, Baker. Cool. So 8 over root 3 units by 32/3. Look at that. There's our maximized area inside of this thing. Now, this particular problem, can you think of where you would ever use this? Like why somebody would ever do this? It's tough, right? Like the good news is that arches are never used in like architecture, right? Nowhere ever has nice arches when they're designing fancy houses or anything. Nobody does that. And gosh, nobody wants light in their house to put a window inside of some big fancy arch while they're trying to make this really fancy house, right? Nobody has ever wanted a window in their house. This is it, right? Like this is one application of it. If I have a fancy archway, and it could be a mosque, because I don't care what we're building, but if you have a fancy arch and you want to put a window in it, you probably want the biggest window that you can have because you want light in your house. This is immediately applicable in the world of architecture. That's the first one that comes to my mind. Cool. All right. We're going to take a quick brain break. Let's brainstorm together. What sort of thing should we make for Miss Sweet? So anybody who's watching the video, just, ladies, we will be looking at the last problem on this worksheet tomorrow, along with getting into some little bit harder ones. But the rest of class today, we are using to make a welcome sign for student teacher tomorrow. So no homework tonight. Hopefully, if you guys play today, you play well, and we'll see you in the video for Thursday. Later.